Alright, let's look at part D of the question. Kinetics of an enzyme catalyzed breakdown of a substrate are investigated. Mechanism is suggested in figure 2.1. So you can see that there's two steps involved here. E refers to the enzyme, S refers to the substrate, ES is the complex, P is the product. Okay, so slow step is actually step number 2. Rate of formation of the complex is rate equals to rate constant forward, concentration of enzyme, concentration of substrate. The rate of breakdown is given by this equation. Rate equals to rate equation for the reverse of step 1 plus rate equation of step 2. Okay. When the rate of formation of the ES, which is the complex, is equals to the rate of breakdown of the ES, the concentration of the ES can be determined. Basically, I am not sure what they just said, but okay, so we just read it off. The expression in terms of ES concentration can be used to deduce the Michaelis constant Km. This constant is a measure of the affinity of an enzyme for its substrate. Okay, so they have given to us the expression there, K reverse plus K2 over Kf. Okay. Write the rate equation for the reverse reaction of step 1 and the rate equation for step 2. Okay, so step 1, we are asked to write the rate equation for the reverse reaction. So looking at step 1, right, the reverse reaction, it will look like ES KR E plus S. Okay, so this is the reverse reaction. The rate is equals to KR ES. Okay, so this is the reverse reaction, and this is the rate equation for the reverse reaction. Okay, so this is the first part. Rate equation of step 2. So rate equation of step 2, we can just look directly at step number 2. The rate equals to K2 ES. Okay, so this is for step 2. Alright, so we're done with part 1. Using your answers to D part 1, which is what we just wrote, and the information given to determine expression, the expression for the concentration of ES. Okay, so what is the information given here? What is the information given? Information given, rate of formation. Let's have a read. Rate of formation equals to rate of breakdown. Okay, because they want us to determine expression for the concentration of ES. Okay, so I think this part is critical. When the rate of formation is equals to the breakdown of ES, the concentration can be determined. Okay, so let's look at the rate of formation of ES and the rate of breakdown of ES. Okay, so the rate of breakdown of the ES is given by rate equation for the reverse and the rate equation of step 2, which is what we did for D part 1. So both of these equation which we have wrote earlier on, right, these two, when they are added together, they give you the rate of breakdown. Okay, then the rate of formation is given here. The rate of formation is given here. Okay, so we got to equate this, right, with our answers in D part 1. Alright, so we just equate these two answers. Let me just solve the question here directly. Okay, so this part here, I'm going to just write it out. KF ES, sorry, KF, this is not, there's no ES here. E concentration, S concentration. We got to equate it to both of these rates. KR ES plus K2 ES. Okay, I hope y'all can see. Let me just adjust this a little bit. Okay, so with each of these in place, let us just rearrange this equation. Rearrange it in terms of ES, yeah. Rearrange, pull out the ES. Give you KR plus K2. KR plus K2. And then KF ES. Okay, so we'll bring this term over. We'll bring this term over to the left hand side. Then we have ES equals to KF E and S over KR plus K2. Alright, so this, ladies and gentlemen, is our expression which we are looking for. Concentration of ES is equals to KF, concentration of E over times concentration of S over KR plus K2. Okay, so this is for part 2. So you do have to read how the question wants you to derive this expression, yeah. Then use your answer in D part 2 to deduce an expression for Km, Michaelis constant, in terms of ES and ES. Okay, Michaelis constant. Let's look at what they given to us. Michaelis constant is KR plus K. Okay, so we're going to relate this expression and we're going to see how it relates to our expression which we have gotten here, because we need to derive an expression in terms of E, S, and ES. Okay, so maybe we'll just write down the expression given by the question. Km equals to KR plus K2 over KF. Okay, so this is the one given by the question. If you invert it, KR plus K2 over K, it is literally equals to okay, this whole expression, right, is actually, if you look at the expression we got from D part 2, this is actually equals to, if we were to invert K, so it's literally equals to E S over E S. Yep, so that's actually it. Okay, you just need to manipulate our expression in D part 2. Okay, so Km as expressed in E, S, and the complex ES. Alright, so it looks a little bit complicated, but I think it is still very much doable.